Hi. So we're going to be looking at the problem of a mass on a spring, and we're going to try to solve for the motion of it as a function of time. So say it starts at x equals 0 here, and we want to solve for x of t of this mass. So I want to take the approach, which is not the standard approach, of solving the second order differential equation with respect to time. So I'll show you what that is, right? So normally F equals ma will be used to show then that ma equals minus kx, right? Where k is the spring constant of the spring, x is the displacement from equilibrium. So that is the force on, that is all the force on the mass. And so that is then equal to the mass times the acceleration of the mass. So acceleration is nothing more than the second derivative of position with respect to time. That's t for time there. And so, all right, this is the standard differential equation that you'll solve for the simple harmonic motion problem. But pretend, or maybe you don't know how to solve that. You don't know how to solve this way, or that you're encountering some other problem that's too complicated to solve in time. Well, then we can rephrase it in terms of position. So let's look at A equals dv dt, right? Acceleration is the derivative of velocity with respect to time. Now we're going to go ahead and we're going to multiply this by 1. So we're going to multiply this by dt dx and by dx dt, right? So that's 1. We'll cancel out these dt's, and we'll get a dv dx and a dx dt. So A equals dv dx, and dx dt is just v. So A is equal to v, the velocity, times the derivative of velocity with respect to position. And now we no longer have to worry about time in our equation at all. Here we go. Go ahead and multiply over the dx's. This is separation of variables, so now we can integrate each side independently. I'm going to go ahead and do indefinite integration here. Sometimes it is clearer to show the bounds, but I kind of prefer not to here. So I'm going to go ahead and put a plus c. And then we're going to have 1/2 mv squared from this integral. Okay, so yeah, there would be a plus c. I'm going to suck it in here. All right, so this is a new constant, and we'll call it good. Now we're going to take this, and what do we have to do from here? I'm going to just rewrite it real quick. 1/2 kx squared plus our constant equals 1/2 the mass times the velocity squared. That's right. That is right. So we're trying to solve for x of t, right? We want x of t. So we have here, we could at least get x of v, but that's not particularly interesting, or it's not what we want. So instead, we can recognize that we actually have another thing to work with here, because we actually know an equation for v. We know that v is the derivative of position with respect to time, which means that dt equals dx over v, for v being a function of x. At least if v is a function of x, then you can integrate this directly with respect to x. That's the point. And it happens to be here because of the way that we started our problem by eliminating time. Okay, that v actually is a function of x. This is just a constant. So v is a function of x. If we could solve for and set, if we can eliminate everything in the way of v and just get v as a function of the other stuff, then we will have an equation between to bring back the time into the picture, basically. And we'll have time as a function of position. So let's go ahead and solve for our v here, right? So I'm going to multiply each by 2 to get rid of these halves to start with. And that gets sucked into a new constant. Beauty of undetermined constants. Now we're going to divide by m. That also gets sucked into a new undetermined constant. Beauty of undetermined constants. Now, we'll just take the square root. Before we do that, let's go ahead and call this km, this k over m, some new number. Like, I like to use chi for some reason. So we'll call that minus chi x squared plus undetermined constant equals v squared. Take the square root of each side, and we have, that's just v. So v equals this stuff. So now we're going to use this, and dt equals dx over v. Right? So we're going to want to integrate this because we have a function of x integrated with respect to x and a function of t with respect to t. So we're going to want to integrate both sides. But before we do that, we want to try to massage this, if you will, to look more like a familiar form that we can look up in an integral table. Because it's been too long since I've taken Calc 2, so I'm not trying to do that manually with trig sub, right? So we will take a look at just this radical here for a second. And what can we do with that to simplify it? Well, we can pull out chi as a square root of chi entirely. We can just do it, right? We can do that because then we divide this term by chi and divide this term by chi, and now c is another new undetermined constant. Would you look at that? Now, we'll take this again, and we're going to take this c, and guess what? We're going to call it c squared. And we can just do that because it's an undetermined constant. So now this c is a new undetermined constant from this c, and thus it's squared. And so, beauty of undetermined constants. Okay, now this right here is a known integral, and we will look at that. So I'm going to write it this way. I'm going to write it c squared minus x squared in here. Okay. So I couldn't get the camera to focus on my calculus book last time I tried this, so I'm going to write right here. This is what we're going to be using. So this is what the table reads. The table shows this. It says that the integral of 1 over the square root of a squared minus u squared du equals the inverse sine of u over a plus constant. And it says this for a greater than 0 for some reason. If a mathematician wants to explain that to me, I'd be happy to hear. But that doesn't actually seem to be very relevant for some reason. So because it just gets squared in here anyway, so I don't understand why that's actually a restriction. Nonetheless, this is precisely the form that we have, with c being a and x being u. So, and you know, we're integrating, of course. So we will now say t equals sine, inverse sine of x over c plus a new undetermined constant. So this is plus c2. I'll call this other one c1. These are different constants. We can't suck one into the other now because one's in the inverse sine. And here we have a function t of x. This is time as a function of position. But what did we want again? We wanted x as a function of time. So, well, now we can just take the sine of each side, right? Well, let's move over our constant here first. So we'll say t plus c2, and I'm going to keep it plus here because it's undetermined, so we suck the minus sign into it. All right. And now we take the sine of each side. I lost a chi here. I lost my square root of chi. This square root of chi was supposed to be out front. Sorry about that. There. So I'm multiplying this by the square root of chi. And then I will suck it into the undetermined constant, and I will leave it as a coefficient of t. So, sorry about that confusion there. There we go. Equals, and now taking the sign of this side is just x over c1. So now we'll take this and multiply each side by c1 and see what we get on the new page. c1 times the sine of square root of chi times t plus c2 equals x, right? Yes, so this is our position as a function of time. And you might look at that and say, oh, that looks familiar. And so that's totally right. It totally is. This is a full solution for the motion of a mass on a spring. You have 1 degree of freedom here for the amplitude that will allow any amplitude for the system, and you have another degree of freedom here for the phase, which allows any starting position. So any starting position, any starting displacement, and any starting velocity of the mass. And so another way that this solution is often seen would be if you were to solve the differential equation with time, then you'll usually get a sine of omega t plus b cosine of omega t. And you have the same degrees of freedom. You've got one here and one here, which this, you know, having a sine plus a cosine with different amplitudes ultimately is reducible to just one trig function with a phase shift. So this here accounts for this, and the point is that it's the full solution. It is the full solution, and it is accurate. Now the question is actually why, and the question is why because if you think back to the function that we took the inverse of, so our time function, or time is a function of x, this is not valid for all x. And so we don't have time. We don't have our function range is only here from, I don't know, like the values, but it would only go from the left bound of our x amplitude and the right bound of our x amplitude when you evaluate this. So then why does... So what I've drawn here to maybe illustrate this is this here was our t as a function of x, and then this is x as a function of t, generally speaking. So our t, it only has, like I'm saying, this range from wherever, you know, if x goes between minus x naught and x naught, with that being the actual amplitude of the mass on the spring, then that inverse function only gives us a time of, like, it only gives us a total time. It only spans a time of half a period of oscillation. And so then when you take the inverse of that, you really only have a function that's mathematically valid at first in that same domain. In the time domain now, where the time spanned in the range. And so then why, in a sense, does it happen that our full solution continues on and does so correctly? Because there's no, because of the fact, like, mathematically, that it's only really valid here, there's no particular reason that it had to do that it had to work so perfectly. And I guess sort of the reason that it ends up completing itself without more work is that we do have a valid half of a period here. And then our solution, being a sinusoid, is perfectly periodic. So if it weren't perfectly periodic and it were like an approximation to one, in the sense that it just didn't continue on waving, but we had a chunk. We had this chunk between this valid domain that it did. Well, then we could manually go ahead and piece together the other half periods onward, because we know from the physical system that it's going to do that. We know that we basically know that we solved for half of a period. And that if we wanted the motion as a function of time way beyond that, well, we could just take those half periods and know that it is oscillatory and stitch them on. And so if you could do that if you didn't have a perfect automatic continuation. But the fact that our solution is exact, like it is, it's perfectly exact and gives us a sign and not some approximation to a sign valid that breaks down outside of the domain as being periodic. Well, then it just automatically stays periodic and it automatically stitches the rest of these half periods on for us. Basically is what's happening. Once you realize that, well, that the physical system allows us to have a time domain extending beyond that half a period, with that rule that it continues on with alternating half periods. And I say alternating because obviously it's got to go back down and such. So, okay, that was my big adventure, was figuring out why this auto magically worked, and that's my understanding of it. So I hope you had fun. I sure did. Yeah, if there's anything, you can feel free to leave comments. My understanding is not perfect on all of this, so I'd love if you could either ask questions or teach me something new that